the rules that we learned for integration in section 5.1, that's it for our class. Those are the only integrations rules we're going to learn. Power rule, adding 1 to the exponent, dividing by the new exponent, as long as the exponent isn't -1. Integrated constant is just that constant times x. Natural log rule for 1 over x or x to the -1 power, and the E rule. And these properties of integrals will still hold. In section 5.2, we learn a strategy called U-Substitution that will take a problem and get it ready for one of these rules using algebra that's different than just multiplying out parentheses, dividing out fractions, moving coefficients outside. So we learn a new technique, and the whole goal of the technique is to take a problem that isn't written for one of these rules, to transform it and make it usable, make one of these rules usable. And I have to be super careful when I set up a problem. If I just randomly make a problem up, the technique that we're going to learn right now, it probably wouldn't work. So these are very carefully constructed problems. And let's just jump into the technique. So if I look at problem, this unnumbered problem, no way in the world I would want to integrate this using the strategy that I had in the last section 5.1, because I need to get rid of the multiplication, and to get rid of something to the 5th power, I'd have to write 5 parentheses in succession and then do a jillion huge foiling. It would be ridiculous. So it's impractical to do the multiplication here. So there's a strategy that's we're going to use. And let me jump into the strategy. It gets very repetitive. At first it's hard, but it's just a sequence of steps that we do over and over again. Eventually it gets not so hard. So how am I going to get this problem set up so I can use the power rule? That's where an exponent of 5 makes me feel like it's a power rule. An exponent of -1 would be an ln, and an e would just stand out. So what am I going to do? I'm going to rewrite the problem so that the parentheses with the exponent is first. So I just took this and wrote it first. This is just a matter of my preference, the way I like to do these problems. If you got taught this by another instructor, they might teach this slightly differently. This just, for me, it makes it easier to follow. If anytime there's a parentheses with an exponent and we're asked to integrate, it's probably going to be the case that we're going to do U-substitution, unless it's very easy to do the multiplication. Here it's not easy to do the multiplication, so I have to learn this trick called U-substitution. Basically, I'm going to take a problem that isn't ready for the power rule that has x's, turn it into a problem that's ready for the power rule that has u's, use the power rule, and then get rid of the u's and make them x's. Step 1, rewrite the problem with the parentheses first. Step 2, I let u be whatever inside the parentheses. Anytime I have a problem with a parentheses that is really impractical to multiply out, I'm going to simplify the problem or integrate the problem by U-substitution. And always, 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 if there's a parentheses with an exponent, I let u be the inside of the parentheses with the exponent. Well, now what am I going to do? I'm going to rewrite this problem. Instead of saying 5x squared minus 4 to the 5th times 10x dx, I'm going to rewrite it, but I'm not going to have 5x squared minus 4. I'm going to replace the u with the 5x squared minus 4. This makes it so it's a parentheses isn't necessary. U to the 5th power with or without a parentheses is equal to u to the 5th power. So step 1, get the parentheses with the exponent, if there is one, written first. Step 2, let u be the contents inside the parentheses. Done and done. Change the problem so that the parentheses is done with the u. So first step, rewrote it with the parentheses first, picked a value for u, rewrote the problem so that it had that u. Perfect. Now I'm going to need to find the derivative. So u, I made equal to 5x squared minus 4. And I need to take the derivative of this. I wrote very formal symbolism here. Let me scrub that and just do a generic derivative. On this side, the derivative of 5x squared is 10x. The derivative of minus 4 is 0. So the right-hand side, the derivative is just 10x. Earlier in the semester, sometimes we did derivatives with y's, and I wrote dy dx for the form of the integral. I need that here. I need to get a dx into this because the integral symbol needs a dx. So the derivative of u is just 1, and I'm going to tack on and say it's du dx. Just like if there was a y here, I would say it's dy dx. So each time I do the integral of the u, it's going to be du dx because it's an integral of 1. I took the derivative of u with respect to x if I wanted to be more specific. So I found du dx, not good enough. What do I need to do with that dx? I need to clear the fraction by multiplying both sides by dx. So I'm going to multiply the left side and the right side by dx. Don't really have room to write it on the right side over here, so I just wrote it where it fits, but both sides I multiply by dx. And what happens now? This dx and that dx cancels. That leaves me with du equals 10x dx. So let me see what I've done so far. I rewrote the problem with the parentheses first, let u be the inside of the parentheses, rewrote the problem so that the parentheses was gone and changed to a u. Now I found the derivative of u and did a bunch of algebra. Did all the algebra that's on this sheet a little bit quicker. I have du is 10x dx. This is a good place to be right now. The place I'm at right now is I have rewritten the problem so that it says u to the 5th times 10x dx. Well, the whole reason we do the U-substitution is so I can get rid of the x part. I can't integrate with two variables, and, well, 10x dx is equal to du. So what am I going to do? I'm going to take that 10x dx and I'm going to replace it with du. This now is ready for the power rule, because the power rule allows me, even if the variable is not x, if it's just a single variable to an exponent, add 1 to the exponent, so now I can integrate this. It's set up perfectly for the power rule. Single variable, even though it's not an x, I'm going to add 1 to the exponent, multiply by a fraction that has 1 over the new exponent in its denominator, so 1 over 6, and tack on the plus c. So now I've integrated using the power rule. Almost done. My original problem doesn't have u's in it. I've integrated using the power rule by doing some trickery to get the problem written so it was usable by the power rule. But this u, that's no good. What do I need to do? I need to change the u back to 5x squared minus 4, and I really need to think of it being in that parentheses. I need to think of this problem as the parentheses version of the u, like that. And simply I take this u, write it as that 5x squared minus 4, and that's my answer. Doesn't seem hard to me. It's mind-bogglingly crazy at when you first learn this. I remember Dr. Moore, because I took my calculus at GCC, Nadine Moore, who retired 15 years ago. Anyways, I remember her teaching this to me, and it didn't feel like it was legal, and it took me forever to understand it. I am good enough to be a math major in grad school, so if I didn't understand it that easy, it's going to take some doing to understand it. But once we do more of these, it's just repetitive, over and over and over again. The steps repeat every single time. They don't vary at all. Essentially, it's just repetition, repetition, just getting good at the repetition. So let's do another problem. Essentially the same problem, but it has the one other twist that could come up. So I have a parentheses with an exponent. No way I'm going to clear that parentheses. I'm going to integrate by U-substitution. Anytime I have a parentheses with an exponent, first step I do is I write that parentheses with an exponent first. Just makes the substitution at the end so much easier for me. So first step, if there's a parentheses with an exponent and it's not written first, write that parentheses with the exponent first. Done. Second step, same second step. Anytime I have a parentheses with an exponent that I don't want to clear by multiplication, I always let u be the inside of that parentheses 100% of the time. That allows me to rewrite the problem. How do I rewrite the problem? I take the rest of the junk, the exponent of 5 and the 20x dx, I leave them alone. But that 5x squared minus 4, the inside of the parentheses that I said I'm going to let u be that, I change to u. Don't need the parentheses so much, so when I rewrite it, I write it without the parentheses. I'm going to insert that parentheses back at the end, but don't need it right now. So that's my rewrite. Now I have an integral that has both u's and x's. I have no idea how to integrate with multivariables. It is possible, but not until you get higher in calculus. So let's get it rewritten. How do we get it rewritten? I need to get rid of this 20x dx using the derivative of the u. So I take the u, and I'm going to find its derivative with respect to x. Always on the left-hand side, I'm just going to say du dx, taking the derivative of u with respect to x, and the derivative comes out to be 1. On the right-hand side, the derivative of 5x squared is 10x. The derivative of minus 4 is 0. So I rewrote the problem with the u. Now I'm going to take the derivative of the u, and I always multiply to clear the fraction. Just exactly like I did in the last problem. I get du is 10x dx. That was good for the last problem, because in the last problem, this stray part was 10x dx. It was a good thing. In this problem, not so good. The reason not so good, because I need to replace 20x dx. Well, I can get a 20x dx with not a lot of work. So this du equals to 10x dx that I'm trying now to make the problem only have u's. Well, I can't replace a 10x dx with a du, so let me try to get a 20x dx. So this problem where I have du, or this equation, equal to 10x dx, not good enough to replace a 20x dx. Not so hard to change a 10x dx into a 20x dx. I just multiply by 2. So I'll multiply the du by 2 and the 10x dx by 2, and I get 2 du equals 20x dx. So what does that allow me to do? That allows me to take the rewrite that I did, and that 20x dx, what do? I change it to 2 du, because 20x dx is equal to 2 du. That's what I'm going to want to integrate, but I can't integrate that just yet because it has a coefficient in hiding. This u to the 5th times 2 du, multiplication is commutative, so I can write that as 2u to the 5th du. So I'm in a good position right now. I have the problem with a single variable, and it's almost ready to integrate using the power rule. How am I going to integrate it using the power rule? Well, first I'm going to bring the 2 out front. Now I can use the power rule. I just have a single variable with an exponent. So let me integrate that now. And how do I integrate that? I add 1 to the exponent. I'm going to get a u to the 6th. Multiply by a fraction that has 1 over that new exponent. In this case, it's going to be 1/6. Have the plus c. The coefficient of 2 is going to cancel out with that 1/6. 2 will cancel with the 6. The 2 will become a 1. The 6 will become a 3. And that's going to give me 1/3 u to the 6th plus c. Maybe it's nice to think of that u with the parentheses. It's not really necessary until we get to the last step to have a parentheses. I've done the integration. I used one of the only rules I have. The power rule is one of the only rules that I have. And now what do I need to do? Simple. I need to get rid of that u by changing the u to 5x squared minus 4, because that's how I set up the u. I set it up as 5x squared minus 4. So in the integral that I figured out, I changed the u to a 5x squared minus 4, and I really need it in a parentheses. That's the answer. Works just as well when I have when I have e's. So if I have a problem with an e, and it's not just a naked e to the x, the only kind of e I know how to integrate is just a generic e to the x power. Can't have e to the 4x cubed power. This is another U-substitution. E's without an exponent of just x, I need to write it and do U-substitution. Just like parentheses with exponents, I'm going to rewrite the problem with the e first. So in the first two problems I did, there was parentheses with exponents, and I didn't want to do the multiplication, so I used U-substitution. Any e problem, if the exponent isn't just an x, it's U-substitution. Step 1, write the problem with the e first. That's what I've done. And then I have to decide on the u. Parentheses with exponents, the u is always the inside of the parentheses with the exponents. E problems, u was always the exponent of the e. So I'm going to let u be the exponent of the e, and I'm going to rewrite this problem as e to the u, and then I have this ugly 12x squared dx that I need to manipulate the derivative of the u so I can substitute. So this is the only hard part, is taking the u, finding its derivative, making its derivative match with what's there so that you can get rid of the x's. So that's the next step. So I've rewritten the problem. Now I'm going to find the derivative of this u. And when I find the derivative, I need to write it as du dx 100% of the time. So I'm going to say du dx on the left-hand side. Right-hand side, the derivative 3 times 4 is 12. Lose 1 from the exponent and get 12x squared. There's my 12x squared. I just need to get the dx involved. How do I get the dx involved? Multiply both sides by dx. Cancel, cancel, and I get du equals 12x squared dx. So my goal is always to write the piece that's going to turn into the u first. The e was going to have a u, so I wrote it first. In the first two problems, the parentheses with the exponent was going to have a u. I wrote it first. Then pick out the e, pick out the u. The u is, if you have a parentheses with the exponent, it's the inside of the parentheses. If it's an e, the u is the exponent. Rewrite the problem with the u. Now I've got u's and x's, no good. U's I'm going to leave. The x's I'm going to get rid of. How do I get rid of them? I take the u that I created, find its derivative, and try to match up this perfectly. If it matches up perfectly, I don't need to multiply by a number to make it match up. If it doesn't match up perfectly, then it has to be set up so you can multiply by a number to make it match up. But this matches up perfectly. So now I'm ready to do my substitution. So into this problem, that is e to the u times 12x squared dx, well, heck, I just figured out that du is equal to 12x squared dx. So for this 12x squared dx, I'm going to change it to just generic du. Good thing, that's the easiest kind of integral. E to just a generic power with a single variable without a coefficient or an exponent, it is its own integral. So the integral of e to the u is just e to the u, just like the integral of e to the x is e to the x. But I can't have u's in my answer when my problem didn't start with u's, so I need to do that replacement. And the exponent kind of works like a parentheses. So when I do the replacement by taking the exponent of u and changing it to 4x cubed, because that's what I picked for u, I don't need a parentheses like I do in the exponent problems that aren't the e problems. So it's it's repetitive 100% of the time. Rewrite it with the piece you're going to make the u first. Rewrite it with the piece that's changing into the u with its u. Use whatever you make for u, find its derivative to try to replace the rest of this x part to make the problem only have u's. Once you get the problem replaced, it's just going to be a one-step power rule, e rule, or ln rule to integrate. And then get the problem so it's back to only having the variable. Alrighty, So let's walk through problem. They're unnumbered. Walk through this unnumbered problem. It's an E problem. E problems, if the exponent isn't just a naked x, I gotta use U-substitution. What do I do? First, I write the piece that I'm gonna make the U, which is gonna be the exponent of the E first. Should be 2x squared. So I just rewrote the problem with the e to the 4x cubed first, and what should have been 2x squared written second, followed by the dx. 100% of time, my lord, I don't know. Oh, this is supposed to be 12. Let me just do this on another sheet of paper because I'm not digging what I've got some typos going here. I was changing the problem probably and I didn't catch the change. So let's look at, if this was the problem, I'm asked to integrate 12. I don't want that. I think I do want 2x squared. Sorry. My sheet is messed up and it's messing up my mind and what I really want to show here. So this is what I want to show. The 2 is good. I'll clean this up after I shut the video off. So, because it's not just a generic e to the x, I'm going to write the e part first and be bound to U-substitution. So I have an e to the 4x cubed and then a 2x squared dx as the pieces that I'm going to have to tend to. Always, if it's not a e to the x problem, I have to do U-substitution, and 100% of the time I let the e be the exponent of the u. I let the u be the exponent of the e. This will allow me to rewrite the problem as e to the u. I don't need a times sign, but I'm emphasizing times 2x squared dx. It's always get the problem written so that what I'm going to change to the u is written first. In this case, it was an e that needed to be written first. E problems, the u was always, always, always the exponent of the u. Now, I have the problem with u's and x's. I need to use the derivative of u to get rid of that. Last trick. So u is 4x cubed. Let me do its derivative. Du dx, and then the derivative of 4x cubed is 12x squared. I'm going to multiply both sides by dx. That's going to give me du equals to 12x squared dx. This is not good. I see the x squared dx, that's good, but this 12 and this 2 aren't the same. So how do I get this 12 to be a 2? Well, 12 divided by 6 is 2. I better do multiplication because it's going to make it easier. So to turn this 12 into a 2, I could either divide by 6 or multiply by 1/6. It's going to be easier for our purposes if I multiply by 1/6, because if I do 1/6 times 12, it's going to show up this morning. If I do 1/6 times 12, you get 2. So I'm multiplying both sides by 1/6 with my whole goal of getting rid of 2x squared dx. To turn a 12 into a 2, I need to divide by 6, which is equivalent to multiplying by 1/6. So this is going to give me 1/6 du equals 2x squared dx. This is a good place to be. So I'm doing all the hard work is manipulating to try to get the x part here to match up with the x part that's left. Now these match. I'm trying to get rid of a 2x squared dx. Well, I know exactly what I can replace 2x squared dx with. I can replace it with 1/6 du. So I can rewrite this problem as the integral of e to the u, and in place of 2x squared dx, make it 1/6 du. This is a coefficient in hiding. I'm going to pass it through the logarithm, through the integral. Why do I keep calling them logarithms? I have no idea. pass it through and get 1/6 times e to the u du. That is its own integral. E is its own integral if the exponent is just a letter to the first, 1x to the first power, 1u to the first power. So this integrates to its own self, and I get the plus c. Not good enough because my answer can't have u's in it because the original problem didn't have u's. How do I get rid of the u's? Well, I do that unwinding of my u. I'm going to change the u back to 4x cubed. So that's 4 problems. Let's do one that turns into a natural log. And I'm going to, my sheet, when I font it up sometimes, not so good. So let me just do this on my own paper. So it's in the writing that I want to do this. And let me go through the steps, and then we'll probably break into a part 2. We'll actually do the homework. So if I want to integrate 16 over 4x minus 3, I can actually write it. If I wanted to integrate 16 over 4x minus 3 dx, this fraction has a binomial in it. I can't break this up into 16 over 4x and 16 over minus 3. That's illegal. What we did in the last section, you need a monomial in the denominator. So I need to get this rewritten to handle u's. And what I'm going to think of this as, I'm going to think of the denominator as having a parentheses with an exponent of 1. And I'm going to use the strategy that we learned in section 5.1 to take fractions and make them have negative exponents. A little more complicated here because the denominator is a little more complicated, but not so bad. So I can rewrite this problem with a negative exponent. So if I have fractions that I can't clear because it has a binomial or even more than a binomial in the denominator, then I'm going to take the whole denominator, bring it up to the numerator by encapsulating it in a parentheses and making the exponent negative. Now this is going to be just like our first 2 examples. I have a parentheses with an exponent, so I'm going to rewrite with the parentheses with the exponent first. This is just my preference. Not everybody would do this, but it just makes sense to me. It just works. It makes things so repetitive, which we need here. There's my rewrite. So there's only 2 choices for u's. If I have an e problem, the u is the exponent of the e. If I have a parentheses with an exponent, the u is the parentheses with the exponent. So what am I going to do? I'm going to let u be the parentheses, the inside of the parentheses, with the exponent. That will allow me to take the problem and rewrite it. I really don't need the parentheses anymore, but I could have the parentheses if I care to. That will allow me to rewrite the problem. I'll skip the parentheses, it's not necessary. But as u to the negative 1 times 16 dx. I need to get that 16 dx changed to u's. How do I do that? I'm going to take the derivative here. I'm going to write du dx, the derivative of u with respect to x. And then on the right-hand side, the derivative of 4x is just 4. The derivative of minus 3 is 0, so the right-hand side is just 4. Often I do this step without showing it. I might have just written this line, du equals to 4 dx, rather than doing the multiplication that I've just done. It's proper to do the multiplication, but if you can go from there to there, that just makes sense to do. It's what normally is done. I look at this 4 dx. If it was exactly that 16 dx, I'd do my substitution. If not, I have to multiply or divide, which is multiplying by a fraction, to make it fit. I'm going to multiply by 4 to make it fit. This is going to give me 4 du equals 16 dx. That's what I'm going to substitute. So in place of my 16 dx, I'm going to put 4 du because those are equal to each other. 4 du is equal to 16 dx. So I can rewrite this problem as u to the negative 1 times 4 du. 4 is considered as a coefficient. I'm going to pass it through and make this 4 times the integral of u to the negative 1 du. When I have negative 1 exponents, those are ln's. The x to the negative 1 integrates to the ln of x. U to the negative 1 is going to integrate to the ln of u. So this is going to turn into 4 times the natural log, technically, of the absolute value of u plus c. Almost done. I can't have an answer with u's because my original problem started with x's. What do I need to do? I need to change the u back to what I started it off as, and in this case it's 4x minus 3, and the absolute value symbol in the formula works as the parentheses. So that will be my answer for that example. There isn't going to be anything at all new when I go to do the actual homework problems. There's nothing new. We've covered every single trick in these warm-ups, so hopefully that you could maybe even jump into those and try to do the problems without even watching me do them. That would be fantastic, but I'll do a bunch of even ones if you need to see more practice.